Hi, this is a video on how to make a nomogram from the RMS package. I have a Shiny app that works as a GUI and uses quite a bit of the RMS package's functionality, but the video that I do have on a nomogram that I made a few years ago doesn't really give a lot of information on what a nomogram is, and it doesn't give any examples of how to interpret the nomogram. So I decided to go ahead and make a new video, and that's what I'll cover here. And so I'll cover 4 examples of how to make nomograms and how to interpret them, and I'll begin now. So this is RStudio, and I have my code for my Shiny app, and I'll start it now. So this is loading my Shiny app. I've already selected data from 4 examples. One is the empty cars data set. That's a default data in R's base program. The other 3 come from Frank Harrell's data repository. I'll put links in below, and I'll use those as our main examples. So let's begin with the empty cars data set, just to give you an idea of what a nomogram is. In my Shiny app, I have at number 1, in box number 1 in the top left, we have the empty cars data set. And I have some various defaults. One of them at step 2 is to not begin our model yet. For number 3, I'm going to select the outcome. I'm going to leave it at mpg, miles per gallon. We'll select some predictors such as the number of cylinders, horsepower, and weight. I'll go back to number 5. I have a linear model, or ordinary least squares, or multiple linear regression. 3 different ways to refer to the same type of model, and that's the default. So I'm going to leave it as it is. Go back to number 2, click yes. This runs my model. I have the coefficients in the output below. So I'm going to go to the tab named Nomogram, and that's at the top right in my display. Okay, so it by default is going to create a nomogram for me. And at the very top we have points, and those are associated with each predictor. I do have a box that selects the variable label size. So it's probably a little bit tough to see what those variable names are on the left. I'm going to increase that to about 3. So in that top row, that represents points that are assigned to each predictor for the specific value. And it ranges on the top from 0 to 100. And then we have 3 coefficients, or 3 predictors: the number of cylinders, the car's horsepower, and the car's weight. This is from the 1973 and 1974 data set on car performance. And the outcome I chose was miles per gallon. So we'll see what a nomogram does is it's a way that we can hand calculate our predicted outcome for miles per gallon based on various values for each of these 3 predictors. It's a really great way to show someone how your model works. In different models we might relax the assumptions of linearity and additivity. In doing that, we would create nonlinear terms. So if you've done a regression where maybe age is a predictor and you expect it not to be have a completely linear trend between your predictor age and whatever outcome you're looking at. If there's nonlinearity, which often happens in data, you'd maybe put it in a squared term. For the analyses that I'm going to do ahead, I'm going to use splines, and you can find that in Frank Harrell's text, which I will also put in the link below. And those are piecewise polynomials, similar to a squared term, but we're allowing it to bend at certain points in the distribution. But we have a very straightforward model. It's a linear model. It's additive. So that means we don't have interactions. So it's easier to see these trends and to work with this data. But let's just give you a demo on how this works. So maybe if we have a car that has 4 cylinders, we look up to the top row where where it has the bar for points, and above 4 cylinders we see it's 30 points. And maybe our horsepower is about 100. So we'd look up, and maybe that's about, say, 37.5. And the car weight would expect it to probably be on the lower side. So let's go up to a value of 2, and that represents 2,000 pounds. And we'll say that's about 87.5 or 88. Okay, so we'll sum up the 30 points from cylinders, 37.5 from a 100 horsepower car, so that's 67.5. The weight, we're going to say it's about 88. My math's not so good, so I'm going to go up to the Describe tab. I could just do that here, but I also want to show you this because if you're new to the RMS package, what you can do is use this tab to run simple commands, and one of them is how you get Frank Harrell's data. You type in get capital H data, and our next example will be the forced expiratory volume data. And so what this is doing, it's loading the FEV data from Frank Harrell's data repository. We'll also do this for the Titanic 3 data, and then we'll also do it for the prostate data, which will be in a survival model that we'll look at last. If you just run the command, you can see where that data actually comes from, and this is the website HBiostat. That's Frank Harrell's website and his data repository. Okay, but let's go back to that example for the nomogram. Again, we looked at a car with 4 cylinders, the horsepower at about 100, and the weight at about 2,000 pounds. So if we sum up the associated points for each predictor, it comes out to 155 total points. So we go down to the bottom 2 rows in this graph. We have the second from the bottom row that represents the total points. So let's go over to about 155 points. That's about in the middle. So if we look down to what our linear predictor value is, that gives you, I'd say, about 27 predicted miles per gallon for that car that has those values that we mentioned above. And so that's what a nomogram does. It allows us to get predicted values for each of our different variables, and we can then try out different predictor values that represent a different, in our example, different types of cars. So maybe we have, if we wanted to know what an 8-cylinder car that has about 300 horsepower and weighs maybe in at 3,000 pounds, maybe that's for a sports car, we can get an idea of what that predicted miles per gallon is. In this GUI I have below, we have the output associated with that, with each has the points associated with each predictor value. So rather than scrolling above to kind of guess what it is based on a visual look, what you could do is just go down below and get those points that are associated with each of the predictor values. Okay, so this was kind of a straightforward model. There's no nonlinearity or interactions in this model. So let's look at one that does have that. So we're going to go back to the model builder. I'm going to turn off the model. I'm going to turn that number 2 to no. For number 1, I'm going to type in FEV, and that's the forced expiratory volume data. And this is a breathing test. It's how many liters of air can we exhale in 1 second. And we're actually looking at pediatric data. And that might be helpful now because with COVID, we're seeing more breathing tests or assessments on lung capacity after experiencing COVID. And again, this data is for pediatric patients. The ages, the maximum age in this data set is, I believe, a 19-year-old. So let's begin. We're going to go to number 3. I'm going to select FEV as the outcome. That's that FEV value. We're going to use the predictors age, height, sex, and smoking. We're going to leave it as a linear model. I'm going to relax the assumptions of linearity and additivity. And so I'm going to go to box 11. And I'm going to add splines, which allow the model to have nonlinear terms. Clicking yes. And I will use the continuous predictors of height and age. And because I'm using an interaction, I'm going to turn box 13 to a value of yes. And that from that answer, or from that question, I'm going to give the answer of yes. And for 14, I'm going to go to the plus sign between age and sex, and I'm going to convert that plus sign to an asterisk, which represents a product or a multiplication term. RCS, that is a restricted cubic spline. Age is the predictor, and we're allowing for 5 knots. And I'm going to go ahead and run the model. And so here's our output. So you'll notice that for height and age, they have multiple rows, and the subsequent rows represent the values, or the coefficients for each of the knots. Restricted cubic splines have use the interior knots. So for a 5-knot model, it's going to use the 3 interior knots. And I have splines for height and age, and I do have an interaction between age and sex. So as you can see, we have just 4 predictors, but when we look at the different coefficients for the model, it makes it look more complicated. We do get a lot of information from using nonlinear terms and interactions, especially since we know in the literature that there is an interaction between age and sex, especially at the for the period at puberty. Boys and girls do have different. We begin to see bigger distinctions in their FEV levels at around the age of 12 and above, and that fits what's in the literature. So those interactions which we see here, and that between age and sex, that's a significant interaction, and it's backed up by past research. But as you can imagine, to review this with the client, that might take more effort than it's worth, when knowing that we do have nomograms to aid us in that. So rather than reviewing each of these coefficients, we're going to go over to the nomogram. But before we do that, I'm going to show you the partial prediction tab. Below we have partial predictions to show our interactions. So at box 1, I'm going to leave age as our continuous predictor. For box 2, our factor is going to be sex, and we're going to, for number 3, we're going to answer yes so we can get confidence bands. We're going to select line colors. I'm just going to use red and blue. Those are the colors for males and females. For numbers, I'm going to leave 5 blank. Number 6, we're going to go ahead and create the plot. And so this is what we're seeing for boys and girls in this graph. And for graphs, you can just right click and copy the image. If you wanted to paste it into a Word file or a PowerPoint, you just click copy image and then press Control V to paste it into your document. But we can see on the x-axis we're looking at age, the y-axis we're looking at predicted values, and we see the predicted values are fairly similar for the first 10 years. But after that, you do see around the ages of 11 or 12, you do see significant differences between males and females, and it could be due to maybe boys are growing faster than girls at that age, as well as maybe other physiological differences at that age. Maybe boys have more lung capacity or bigger lungs as they grow older. But you do see that from the ages of 0 to 10, not a lot of difference between boys and girls in terms of the number of liters that they can exhale in 1 second. But after about 12, we do see differences between boys and girls, and this makes sense in the literature. So that's why we would need to have some nonlinearity or interactions, and in our case, both, for this model. I'm going to go back just to the model, see what the R-square is for it. We see the R-square is about 0.807. So let's now go to the nomogram. And we see again on that top row we have points. We have the predictor height. Because we had an interaction, we have two bars, age for females and age for males. We have the predictor smoke, which represents if they smoke or not, And the bottom two rows are the total points and the linear predictor. That once we sum the total points, we can then find where that value is on the linear predictor to get an idea of what our specific patient might have as their total or as their predicted FEV level. So let's do an example. We're going to look at a child that is 64 inches tall. So a child that's 5 feet 4 inches. If we look up, they're probably about 52 or 54 points. We're going to say this is a boy that is about 12 years old. So that looks like they're about 54 or 55 points. Or I'm sorry, if we look up, 12 is about, above that is 20 points. And then if we go to smoking, we're going to say this 12-year-old boy is a non-smoker. And so if we look up, that's about 5 points. So now we'll sum up the age, or the height is 64 inches. It's about 54 points. The age for the boy is 12, so we'll say 55 points. And being a non-smoker is about 5 points. So over for the total, we're going to say they're about 114 points for their total points. If we go over to that row second from the bottom and find 114 points, we're going to say their linear predictor is 4.25 about. It's just to let you know, a value of 4 is considered would be considered a healthy lung capacity for an adult. So this 12-year-old boy that's 5'4" has the lung capacity similar to a healthy adult. And there's some important things to point out about this graph. If you look at, for example, height, if you look at the values, the spacing between each of the values, it looks like it's about 2 points. So in that first tick, it has it's above the value of 46. Then we see 48, 50, 52, and so on. But right around 66 to 68, we can visibly tell that the space between 64 and 66 isn't quite the same as, say, for example, 46 to 48 or 44 to 46. It appears that as their height gets bigger, then we're seeing a bigger space between our predicted FEV level. And so that would make sense that if as children are growing and their lungs are able to exhale a greater volume of air, that age may kind of take off at that point, that it would make a difference in that FEV level. And that's partially what we would expect with that nonlinear trend. So we'll just go back to that graph. And we can look at height, and we can kind of see that the incline in that trend in the beginning is not as steep as what we see for taller patients. We see this trend increase at a greater pace in these for children that are at taller heights. So this does look more like more of a linear trend, but if we look at the rate of incline for the lower heights versus the high, I guess, versus the bigger heights, we do see a difference. And we can see it a little bit more clearly here that as children get older and as they get taller, we're starting to see increases in FEV levels. So maybe with the growth spurt later on in their childhood, patients do have greater FEV levels. So this is an example of nonlinearity and how we can, rather than going back to the model coefficients, we can get some of the same information out of these different out of the different components within that our nonlinear term for height and age. But it's probably easier just to create a nomogram that accounts for that nonlinearity, and we can then show that with the differences between patients that are older and have bigger height values compared to those that are younger. And another important thing to point out is that what we can see here is that height has values that stretch that entire range of points from 0 to 100. So the predictors that have the bars that spread out the most are the predictors that also have the most impact on that outcome. So for height, every value of height really counts. When we look at smoking, we can tell that that difference isn't that big of a difference between smokers and non-smokers, and part of the reason is that for our smokers, they didn't really start smoking until later on in life. So our smokers are really our oldest smokers, and these are also our tallest smokers. So they have, just because they're older and taller, they do have bigger FEV values. But we can tell the predictors with the bars furthest to the right, or they have the widest spread in scores. Each of these values really counts, whereas the ones that have lower values or narrower bars, those predictors don't have as much impact on the outcome as predictors like height. And but this in how we would deal with the interaction, we get two separate bars. We have a bar for females and a bar for males. So we have an interaction between between age and sex. And how we can account for that in the nomogram is that we get two different bars that we can total the points from. Okay, so let's try another example. We're going to use the Titanic data. At number 3, we'll put the outcome as survived. We use passenger class, sex, age, and sibling spouse, the number of siblings or spouses. And change that to a logistic model. And we'll go ahead and use splines for age. And we'll put an interaction between age and sex. You're using the asterisk between those two variables to indicate an interaction between the two. And we'll go ahead and run the model. And remember, for at 11 and 13 we changed that dialog box to the value of yes, to indicate that yes, we do want splines, and yes, we do want to update the model formula. And we did that by putting in the interaction term. And we can see these multiple rows for age because of the knots that we have. We allowed for nonlinearity by using a spline term. And then we have the age by sex interaction. And we have it indicated for each of our different piecewise polynomials. So let's go back to the Nomogram tab. Okay, so in this graph gave us our standard nomogram. We have the row for points, our different predictors, the two rows for total points, and the linear predictor that we can use to get a predicted value. You'll notice that it ranges from -6 to 4. But we might also want to look at a predicted value for this each of our passengers. And so how we can get a row for predicted probabilities, we go up to number 8, change the no to yes to answer the question, do you want to create a new nomogram? We'll click yes because it's going to give us a nomogram with a value, or in our case predicted values, and these are probabilities. And in it we can see it ranges from 0.1 to 0.9. And so this gives us the probability of survival, or the probability that they survived in this data set. So let's try an example. We're going to look at a female who is an infant or a newborn. We're going to say that that she is 0 years old. And so we see that above that 0, the points would equal 90. We're going to say this patient had a ticket for the 3rd class. So we see above that the points equal 0. And the number of sibling spouses that this passenger had was 0. She was an only child, or at least she had no other siblings on board with her. So that sums up to about 163. We're going to say that point is 63 and the total is 163. So we're going to go down to total points. We're going to find where about 163 is, and we see that the linear predictor is about 1.9, but we're really interested in that predicted value, and we're going to say that this passenger had about a predicted value. Their probability was 0.87, or 87%. but and this is an actual passenger. She was the last passenger to survive. She was a newborn or an infant when her parents brought her on the Titanic. I don't believe her father survived, but she and her mother both survived, and I can't remember her name, but the last passenger was this infant that was from the third class. That was the last remaining passenger to survive late in age. She had a long, healthy life. But we can also use the values below for the predictor value and points, and we can sum that up to get that value. I'm probably a little off, but we can say that she had a very high probability of survival. And from looking at this data, we can say that for women, for females, their age was important because it was associated with higher survivability, but their age as for females was higher. For males, your age really did count, but it really counted if you're younger. You can see that on the far left, the age that we see below 0 points is for an 80-year-old, and below 20, between 20 and 80, there wasn't much. You didn't really have that high of a chance of surviving, or there wasn't a big benefit from that. We do see that, you do notice that 30 is to the right of 20. So let's go back to the partial predictions. We're going to get a closer look at our interaction between age and sex. For that blue line with the confidence band, that represents the age trend for males. And you can see right around 30, you can see there's an increase in that trend. And so maybe there's a greater likelihood of surviving for males that were probably maybe around the age of having children. And so maybe they're having their first child, or maybe they've had a recent newborn. So you do see that what we might think of as fathers having a slightly increased chance of surviving the Titanic. So if we go back to the nomogram, if you notice that 30-year-olds have a higher chance of surviving than a 20-year-old, it could be due to that. It could be due to the 30-year-olds having children at that point. Okay, so that's what, and you can get this information, you can get the predicted values on the probability of having survived by going up to number 8. When the default nomogram you get that doesn't have the probability of surviving, you can click yes and get that extra row. Okay, so let's go on to our last example. I'm going to change that to no for now. So we're going to look at the prostate data. We're going to do a Cox proportional hazard model. Let's change number 2 to no for now. While we do the model, D time is the death time. do need to bring up the model. I got this from the code. If you do get the RMS book, it does have the code to do all of the examples in it. And so this is my own code when I first got the book, and I'm going to use that to replicate a survival model that does have a nomogram in the text. Okay, so I'm going to, because this comes out in a browser, I'm going to minimize it, minimize the window, and I'm going to start entering the predictors here. Okay. So we have age, and I can tell on the text I copied on the right that age will have splines. Next is weight, PF, HX, and you can find the code book in the data set. In Frank Harrell's data, he adds labels to it. So when we look at the nomogram later, if you have labels attached to your data set, then you can also you'll also have that in the output that I'll show you in a couple minutes. So let's add the remaining predictors: DBP, EKG, HG, SG, SZ, AP, and BM. Okay, so we have our predictors. I already have 11 set to yes, so I will have splines. We're going to add it for age, weight, SBP, DBP, HG, SG, SZ, AP, and okay, now I'm going to maximize my screen. By default, I'm going to, my code produces splines with 5 knots. I'm going to change it to 4 as Professor Harrell had it in his code or his text. So in my code that I used for this Shiny app, I move all the predictors with splines out to the front, just so it's a little easier for me to do something like this, where I'm going to go through each one and modify the number of knots. For AP, it's has a very, very high positive skew. So I think Professor Harrell added the log term to it to account for that very positively skewed data. Okay. So now we're going to go ahead and run the model. The model is produced below, although looks like I forgot to change it to a Cox proportional hazard model. I'm going to change number 2 to no. Go down to Cox pH with censoring. Above it's Cox pH. That's a proportional hazard model in which all of the cases were able to experience the event. So not all did here, so we're going to use the version that's read as Cox pH with censoring. And I'm going to indicate what my censoring variable is. And we're going to use status not equal to alive. Okay, so now we're going to run the model. Okay, so that text looks correct, or our output looks like it ran smoothly. So now we're going to go over to the Nomogram tab. Okay, so you'll notice right at the beginning we have the error term. Variable limits and transformations are such that an infinite axis value has resulted. Rerun specifying your own limits to variables. So we'll do that for AP. We can see, hopefully you can see the values that I copied over. The log of AP. So we just have a set of values that, because it's so positively skewed, we have values that are just complicated to use in a nomogram. So we're going to specify certain values for AP so that we can get a nomogram that's useful, that has our main values, and doesn't have to deal with these really extreme ranges of values, because we're just limited in what we can see. Okay, so we're gonna go to box number 1. Most of these boxes were designed for survival models like Cox proportional hazards. And so we're looking at data that ranges up to 5 years. We're looking at months, so we're going to change. I have the values of 1 and 2 show up in box 1, 3, and 4. And these are just default values that come out. I do have, I will get predicted probabilities for the mean and median. So I have, on these I have 2 values that show up by default. They don't fit. The 2 values are always going to be 1 and 2, and so they're going to seldom fit the actual data that you're looking at. But it just produces some starting values by default. So let's change 1 to 36, and we're going to change 2 to 50. So we're really looking at 3 and 5 year predictions. At box 2, I could convert the values in months to years. So if we look at, in our example, it's 36 divided by 12. That 12 represents 12 months in a year. So if you have 36 divided by 12 months, that equals 3 years, and we want to look at predictions based on the period of years. So we're going to change 1 to 12. It's going to transform that value. It's going to divide the months that we have in our data into years. And we have median and mean survival times. So I'm going to change that to 3 and 5, because we're now going to be looking at years. Number 1, we actually have it on the scale in the data, which is by months. That's at the 36th and 50th month. We've transformed it from months to year, and now on number 3, we're going to specify on the x-axis that we're going to see in a minute. We're going to change that to 3 and 5. Oh, I'm sorry. So let's, I believe it ranges from 1 to maybe 6. So we're going to see the full range. That's probably a lot more helpful to see the full range rather than the range between our two limits of 3 and 5. Let's just use the full range. So we're going to type in 1:6. That's going to give us that full 6-year range. For number 4, we're getting values back in the year, so by year, so we're going to change that to 3 and 5. And it's for that 3 and 5, they represent years. So at number 5, we're going to change hour, which is just a default value. We can look at hours, days, weeks, months, or years. Since we're looking at 3 and 5 year survival, we're going to change number 5 to year, and that's just part of our text. So we're just doing it for that purpose, for our display purposes. And select variable label size. I have it at 3. I'll leave it there, but I'm pretty sure with the added variables I'm going to have to shrink the label sizes down. But I'll wait until the graph comes up. Okay, so that error that we're having is with the values for AP. And this is really something that's a special case. So far I've only used it for 1 or 2 different things. About 95% of when you use a nomogram for survival models, you won't have to do what I'm going to do next, which is just specify what values we want to look at for AP. Okay. So I have the text saved here. I'm going to copy that. And I'm going to go back to the GUI. And I'm going to add it after fit. Fit represents the model fit. And I added that for our AP predictor. I would like to look at values that range from 0.1 to 0.4. I'm sorry, from 0.1 to 40. It goes 0.1, 0.5, 1, 2, 3, 4, 5, 10, 20, 30, and 40. So I'm in that for that bar, and for the nomogram values, we're going to look at that range, and for those values. Okay, so now because we've updated the nomogram formula, we're going to click yes at number 8, and it produced the nomogram for us. The issue that we had before was that AP had an impossibly wide range of values that would be impossible to represent in this nomogram. So we're going to look at the main ones. We're going to look at the values that we feel count the most. Okay, so on the left side we can see those labels are just a little too big. So I'm going to go back up to number 6. I'm going to decrease them to about 1.5. We can see them a lot better than the default setting of 1. That's not too bad, but we can go up to 1.5. And it's a little bit easier to read, and it's within the limit of what we have in our graph. Okay, so we have the points at the top, like we usually do. We have our predictors below that, and for AP, that is serum prostatic acid phosphatase. And then towards the bottom we have the total points row. We have our linear predictor. We're using Logistic, so those values range from -2.5 to 3. And we have a predicted 3-year survival probability. And we have one for the 5-year survival. And we have on the bottom 2 rows, we have the mean survival time in years, as well as the median survival time in years. And so these are the additional things that we do get out of our survival model. I have an accelerated failure time model in there as well, and it's the same process. But we can see here that, again, it's actually, we have a few predictors that do count quite a bit, such as age and years, the systolic and diastolic blood pressure, weight, the size of the primary tumor. We're looking at prostate cancer, so of course information about the type of cancer, but also the size of the tumor are important to understanding the survival time. Okay, so that was different examples of how to use a nomogram. This is found in the GUI that I made. It's a Shiny app. I'll put the link to where you can find it at, but I would highly recommend looking at Professor Frank Harrell's RMS package. The code with it is very straightforward. Just to run a basic nomogram for any model, the code is nomogram, and then in parentheses you have your model name. It's really straightforward. It gives you all that information, and if you want to add more detail or change the labels, the code for that is also really easy to learn. So I would recommend the RMS package, the regression modeling strategies book. The second edition is out, which is where I got this example and the code that I used to create this GUI. Thank you.